Welcome to class. Today we're going to look at some numerical aspects of partial differential equations and how to implement them in Python. So let's start with section 15.1, Laplace's equation, page 545. So we have Laplace's equation right here, and our goal is to solve these boundary value problems numerically to get an approximation of the solution. Previously, we used Fourier series to find an exact solution as an infinite series, and we also approximated the solution by cutting off the infinite series at finite many terms. But this is a little different. Here we're going to, from the beginning, we try to approximate. Alright, so remember when we did the finite difference equations for ordinary boundary value problems, we learned that the second derivative can be written as u of x plus h minus 2u of x plus u of x minus h. Notice the y is fixed, and we're taking the second partial with respect to x. So this is the difference equation version of the second derivative. And in a similar way, if you just keep x fixed but change y, you get an approximation for the second partial of u with respect to y. So going back to the Laplace equation, we have to add these two, and we're supposed to get 0. So doing so, you get the 5-point approximation, and you get that this term right here, this whole term, is supposed to equal 0. Well, multiplying both sides by h squared, you can ignore the h squared, and our approximation is that this will have to be 0. And this is the basis for the approximation. All right, so we want to approximate our function of two variables. So if we start at the point x, y, then shifting to the right by h, that changes the index I by 1. And if we shift up by h, that changes the index j by 1. And if you go down by h in the x variable, I goes down by 1, and same thing for y and j here. Okay. Alright, so rewriting this using this notation, what we get is a discrete version of the partial differential equation. So just rewriting this using this notation, you get this. Okay, so this will allow us to write many equations that are interrelated, and in theory they can be used to solve for all of these variables. Alright, so what's going on here is, suppose you're at this red point right here. Then solving for u sub ij from the previous page, you get that this is equal to 1/4 of these 4 terms. These 4 terms are the 4 terms that are neighbors with the interior point. So Uij is an interior point here. And these 4 terms correspond to this term, that term, and that term. And what's happening is the average of the values at these 4 points gives you the value of the middle. So the middle can be obtained by averaging the 4 neighbors. Okay, so you need to use double subscripts here because this is a 2-dimensional problem. And each time you shift to the right by h, you're updating the subscript. So suppose we start off at 0, 0, right here. Then this would be P1, 0, P2, 0. So P2, 0 means you've shifted to the right by 2h, and the y value hasn't changed. But if you go up to here, you go to the right by h, and you go up h, that would be P1, 1, P of h comma h. All right. And what I said before about using the 4 neighbors to compute the value of the interior point, so these would be the 4 neighbors of Pij. Left, think of I now in j instead of using h. So I minus 1 to the left, I plus 1 to the right, j plus 1 up, j minus 1 down. All right, so typically we would have boundary conditions, and the boundary conditions would be the value of u along some kind of boundary. All right, so let's take a look at an example. So this is page 546. So we want to solve the Laplacian, the Laplace equation. This is true in the interior of a square, 0, 2, 0, 2. So this is our square here. When x is 0, so the y-axis, for all y, the function is 0. So it's 0 along this whole edge here. When y is 0, for all x, it's 0. So the function is supposed to be 0 along the x-axis here. When x is 2 and y is free to vary, the value of our solution has to be y times 2 minus y. So that would be the function along this edge over here. Only y is important. The x stays fixed. And finally, when y is 2 and x varies, so up here, the function is equal to this function here. Right, so those are the boundary conditions. There's 4 boundary conditions, 1 for each side of the square. Okay, so we basically need to solve for the interior points because we know the boundary points. Those are given. If you plug in to this function here at 1 at 2/3 and then 4/3. So h is 2/3 here. So 2/3, 4/3, 6/3. So if you plug in to these functions, you would get these values. And the point is that the average of the four neighbors of each of these red points has to equal the interior point. But the trouble is you don't know some of the interior points. So you can't simply solve it as you would on a basic algebra problem. All right, so you get equations like this. -4 u11, so that would be the interior point there, is equal to the sum of u21, u12, u01, right here, and u10, right there. So those would be the four neighbors of that point. So when you do this for all of the interior points, you get this system of equations. Now, you can solve this. What you would probably want to do is rewrite these double subscripts as a single subscript. I'll show you that a little later. And then plug it into some kind of linear algebra solver. However, there is an easier way to do this. Because there's double subscripts, the number of variables gets very big. And very quickly you could have thousands and thousands of equations. So this is not the most efficient way to solve it. And in fact, if you make h a little bit smaller, if you turn h into a half rather than 2/3, you get all of these equations. And it's still small enough that you actually can still solve it with a linear algebra solver. But this would be a little difficult. All right, so let's see the easy way to solve this. So just to point out, if you could put those equations in a 9x9 matrix, but you have to rewrite each double subscripted variable as a single one, like x1, x2, x3, x4. That would correspond to a u11, u12, u21. You probably want to write it down here. All right, so the way that we're actually going to solve this is with a technique called the Gauss-Seidel iteration. So we're going to go back to this equation here, this equation 6 right here. And the idea is we're going to start out by guessing values of the interior points, plug in the boundary points, and it's just a guess at first. That will give us an answer, which is not going to be accurate yet, but then you keep on doing this over and over again, and eventually it actually converges to a solution. So I'll explain. So what you could do is first replace the u11, u21, u12, u22. These are the interior points by just normal variables, x1, x2, x3, x4. So we're essentially solving for the interior points. So going back to equation 7, see the interior points are the interior variables at the interior points are the ones with the -4 there. So notice that you can solve for each of these interior points. just move it to the other side and solve for these variables. So let's do that first. And when you do that, we get this. So remember, x1 would be u11, x2 would be u21. These all represent the variable at interior points. Okay, so what you basically do is you start with a guess for x2, x3, start with a guess for all of the variables, x1, x2, x3, and x4. The book uses 0.4 for everything because that's actually the average of all of the boundary values. But I don't believe it really matters much. But you probably wouldn't want to use 0 in some cases. But that probably would work also. Okay, so what you do is you guess a value for each of the 4 variables, and then you plug in to the right side, and you get a new variable here, a new value here. You plug in, and you get a new value, plug in, new value, plug in, and get a new value. Each time you plug in and get a value, you plug it in here, and you keep updating these, going through them over and over again, and what happens is you actually converge to a solution. You actually can solve this without having to do the Gaussian elimination. All right, so let's take a look at how it works. So let's go to Python now and see what's happening there. Okay. So this is part 4 of the notes. So the first thing I did is I coded the 4 boundary conditions. We need 4 functions there. 1 function for each side of the square. So there's the y times 2y. There's the split function here, and 0 on those edges. So I'll show you again what it looks like in the original problem. So once again, here are the 4 functions: 1, 2, 3, and 4. Okay, so I got the 4 functions coded. My square goes from 0 to 2 on the x-axis, 0 to 2 on the y-axis. So that's A, B, C, D. H, in our example, is 2/3. And to find the number of subdivision points, we just use b minus a over h. It turns out it's a square, so n and m are the same, but they don't have to be. Okay, so in order to do this properly, you need to figure out what the interior points are and the exterior points are. So I use Python for this. Python makes it pretty easy. So the interior points are these guys here. Let me print this out for you so you can see. So print extr. All right, I'm going to run it. So see, these are the interior points. Oh, sorry, I printed the exterior. So these are the exterior points. All right, so 0, 0, 0, 1, 0, 2. right? 0, 0, 0, 1, 0, 2, 0, 3. Sorry, 0, 0, 0, 1, 0, okay. So these aren't the actual, when I say like 0, 0, 0, 1, 0, 2, 0, 3, they're not the actual coordinates. They're the subscripts, right? These are the subscripts. So it's really P0, P10, P20, P30. Right. So here are the indices of the points that are on the boundary, the exterior points. Notice they either have a 0 or a 3. They have to have at least one of those numbers to be on the boundary. All right, and the interior are the points in the square that are not exterior. So I use list comprehension here. So to see what these look like. These are the interior points. Notice we have 4 of them. 1, 1, 1, 2, 2, 1, 2, 2. And that's exactly what the red numbers are. Okay. Now, in order to keep track of the variables, I'm actually going to use a dictionary. So use a dictionary here. And the dictionary has double subscripts. And the reason I did this, just because it's easy to use a dictionary, I could have used NumPy and turned it into a two-dimensional array. But this is definitely easier. And you don't have to think as carefully if you do it this way, but it's not going to be as fast. All right, so for ij in the interior points, so for all interior points, we're just setting their values equal to 0.4. That's just like my initial guess. Then for the exterior points here, well, I don't have to guess those because the boundary values always give them to you. They give them to you exactly. And notice to get a boundary, either I is 0, j is 0, I is n, j is m. And remember, n and m are both 3 in this case. All right, so boundary conditions determine the exterior variables. And this is where the work comes in, right here. So I'm going to do this process 50 times. What am I going to do 50 times? I'm going to use the equations to solve for the interior point variables. So notice it's the average of the 4 neighbors that's supposed to equal the interior point. So for every interior point, I get an equation, and sometimes interior points will end up on the right-hand side, but they would have been updated by the previous iteration. So let me see if I can show you what's happening here a little bit. Let me change this to 5. And each time I do this, why don't I print out U, just so you could see what the dictionary looks like. All right, so it starts off as I don't know if you could see this, so much of this. I'll shrink it a little bit. All right, so this is U11 is 0.4, U12 is 0.4, right? Everything is 0.4 except for the boundaries. Okay, then what's happening is after you go through each equation here, you update various ones. So you can see u11 gets updated and becomes 0.2 next. So this is something you'll be able to do by hand if the system is not too long. So this is something you definitely could do on an exam. Not obviously 50 times, but you know, a few times. So let me put this print to you here. Let me put it and show you how it's converging. Alright, so notice the numbers are stabilizing, see? They seem to be stabilizing really fast. The convergence seems to be very, sort of like an exponential. Okay. Alright, let me get rid of this. Alright. Now let's solve this with a smaller value. See if we solve it with 1/2. If you want to see the answer, here's the answer for the variables. And notice that you get the correct answer here. So u11 is 0.1094, u12 is 0.2098. Right, so we get the right answer. Okay. Now, this is a two-variable function. And the way to graph two-variable functions, as you learned in Calculus 3, is as a surface. So here is here's our surface plot. Notice at the boundaries, the graph has to satisfy the boundary conditions. And then the goal is to find the interior points. So to get a better picture, you can make h a little smaller. So let's make h 1/100. Notice it has to think a bit. It's solving for a huge number of variables. I guess roughly 10,000. It might be a little too much for Python. NumPy could probably handle this 10 times as fast. Alright, let me make it a little smaller. We don't really need this level of accuracy. So how about 1/20? Alright, that's done pretty fast. And then let's this is probably why it took so long, because I printed them out. So let me show you. It gets a lot faster. This is the output is what takes forever in Python. So let me get rid of this. See, comment this out. So now I think it's a lot faster. So if we go back to 1/100 again. Only took 3 seconds. So nothing wrong with Python. It's plenty fast. All right. And plotting it. So Looks a little funny there. It's hard to really tell. We probably need a bigger plot. Let's try 1 over 20. Let's say 1 over 10. That might be good enough. Alright, so this part over here may be a little bit of an aberration, but you get the idea of what the graph looks like. So this is how you do a 3D plot here. I'm using NumPy here, of course. So we have our linspace x1, y1. U is going to be the z values. And this is what's called a mesh grid. It gives you x and y that are generated for the set of squares. So this mesh grid gives you the x, y axis. And basically, U is NumPy double array. And I'm just taking the dictionary, which is on the right side, and I'm storing the values into NumPy, because I needed a NumPy to plot it. And this code here will plot a surface of x, y versus u, which is really the z value. All right, and there's our curve. All right, so the last thing I want to show you is the animation, how it works. So here's the heat equation. This is notes part 3. So let's first run it. So you run it. All right, so it's taking a while because it has to generate a movie. And what are we doing here? So we're generating a movie with 2,000 frames. This is an animation with 2,000 frames. The interval looks like it's 20. I'm not sure if that's the time interval or not. We'll try to figure that out soon. Alright, so you can ignore some of this stuff. This is syntax you need to plot. These are the x and y axis here. So x will go from 0 to pi. Y will go from 0 to 110. And you could ignore this line over here. You could ignore this line here. This is just initialization. Here's where the things take place. So we have our linspace from 0 to pi. N is 1,000. We have 1,000 subdivisions. And y is, or 0, it's going to be our y values. It's currently 0. Big N is 50. So I want 50 terms of the infinite series solution. So if you solve the heat equation directly, what you get is this function here. So you get e to the negative n squared t times the sine of nx times this coefficient here, 200 over pi, 200 over n pi times 1 minus 1 to the nth power. Alright, so this is in the notes. This is in the notes, page 55 of the class notes. Alright, so now animate I. Well, what is I? So t is I over 200. So when I goes from 0 to 200, you've completed 1 second. That's what t, when t is 1, that's 1 second has gone by. So animate is a function that's going to get called by the animation. So the animation line is going to keep on changing I. It's going to do 2,000 frames. So I think, I'm not 100% sure, but I think it's going to go from like 0 to 2,000. And but you might want to experiment a little bit. It might be jumping by 20 each time. I'm not 100% sure of that. It's not important anyway. Okay. So when I goes to 2,000, you'll get 10 seconds worth of animations. All right, so let's see where it is. All right, so if we click here, so it finished, and you get this nice blank picture here. Click here, and here's the basic animation. You could change the file name if you like. Let's click over here and download it. Double click on there. Alright, so here is our animation. And it's going to go for about, looks like about 80 seconds or so, 70 seconds almost. Alright, so let's run it. So as you can see, it's cooling down. The heat is dissipating. And it does so in this nice way. And eventually, you have like almost no heat left. Okay. Alright, so now let's see the example with the wave equation. And let me change the file name so that it doesn't delete. Let's call this one wave. So it's the same thing, except I'm using the solution to the wave equation, which is page 68. Alright. Remember, this sum over here is simply summing over the infinite series, but just 50 terms. And I corresponds to a t, and that corresponds to 1/200th of a second. So each frame is 1/200th of a second. The animation is 30 frames per second. So maybe you could do the calculation and figure out exactly how many frames there are and stuff. Alright, so down here you can see Python is running all these different functions. A lot of computer power is needed to create animations. Notice things like L and A those just come from the wave equation. All right, it looks like we're done. And notice the wave animation popped up here on the left. All right. So let's see what it looks like. Let's run it. So here's the string that's stretched. And then it comes back up again. All right, pretty neat. So that's basically it. We'll go over the difference, the finite difference method in class as we try to do it on our calculators.